Welcome back to the Organic Chemistry playlist. In this video, we're looking at nitrogen nucleophiles with respect to ketone and aldehyde chemistry. We're going to look at, okay, how does a primary amine react with a ketone? What does a secondary amine do to a ketone? And then we're going to also look at something called wolff-kishner reduction, which you make a hydrazone and then you reduce it down just to an alkane, which can be synthetically useful in some cases. So we're going to start here with what happens when you react a primary amine with a ketone. Well, what happens is you get something called an imine. An imine looks like this. It's a double-bound nitrogen with an R group coming off of it. It looks a little unfamiliar, okay? And so my reagents here are R and H2, R standing for some carbon group or some other group, right? And the nitrogen's right here. And then it's bound to two hydrogens in acidic conditions. So we want to keep the pH at about 5 here. So just slightly acidic. We want to use something like H2SO4, keeping it without the presence of, say, water, because we know water will form a hydrate. Without the presence of an alcohol, because that, for example, will make stuff like acetals. And we don't want that kind of chemistry. We want nitrogen chemistry. So let's go ahead and show the mechanism for how it works. So we're going to start with our nice little ketone here. And like we saw with oxygen nucleophiles, we're going to see that it's going to pick up a hydrogen ion from solution. So we'll just draw that H+. It's going to pick up that hydrogen and become positively charged. This activates this carbon here to be more positive. It's ready for a nucleophile to attack. And that's exactly what happens in step 2, where our amine comes in and is like, and if you really think about this here, who likes a positive charge more? Well, remember the electronegativity rules, right? That oxygen hates a positive charge because it's more electronegative than, say, nitrogen. Nitrogen is just a tad bit less electronegative and therefore is happier with a positive charge. So they're going to they're going to swap charges by, okay, nitrogen's going to come in and kick up electrons to the oxygen. Okay, and that forms this compound here. So we have OH neutral now. And we have, no electrons there. A tetrasubstituted nitrogen atom, okay? And that has a positive charge. So this is favored, but we can favor it even more, and I'll show you exactly how that's done. We're going to use some sort of basic species. Now this is a species that is not as happy, but it's going to pick up a hydrogen here. It's going to dump electrons onto the nitrogen. And now everything is going to look neutral. And that's good. Okay, so when you get to this step, the molecules are relatively happy from where they were here. Unhappy molecule, somewhat happy molecule. Okay, that's a good thing. This is a decently, now it's not as stable as, say, a ketone, but it's relatively stable. And what happens next in the mechanism, and I'm going to have to curve my arrow here. What happens next is, okay, now oxygen is going to be wanting to leave. And because we're going to want an imine, you might be able to see something here, but before we get to that, let's show that our OH picks up a hydrogen, and we're going to have a water leaving group. It's ready to leave. That water is beyond ready. It is like, get me out of here. So nitrogen is like, okay, oxygen, you have a positive charge. If you want to leave, you can. We'll kick you out and it will be okay. And I'll have a positive charge, but at least you won't, right? Nitrogen's the selfless one. So that's exactly what happens. These electrons fold in, the lone pair on nitrogen. That's that unique ability of nitrogen, is having those lone pairs, but that one set of it. And it just kicks off the H2O. So we lose water, and now we have what's called an imine, but it's not really an imine yet because we have to neutralize it because we have a positive charge on nitrogen, which just comes from another equivalent of our amine coming in and deprotonating our protonated imine to just form the imine. So here we have our imine. That's imine formation from a ketone to an imine using acidic conditions and that amine of interest. So primary amines make imines, all right? And you just have to use acid to get that reaction going. So let's kind of summarize the mechanism before we get into secondary amines. Okay, notice the carbonyl picks up a hydrogen. Nitrogen attacks that center, okay? We get deprotonation. Now the OH picks up a proton. Now OH is not happy, it has a positive charge, so nitrogen comes in, kicks it off. We have a positively charged nitrogen or a protonated imine, and then that imine that protonated amine gets deprotonated by some basic species, say our primary amine in solution, and we're going to get our final product imine. So now let's get into secondary amines and how they react with ketones. So now let's talk about those secondary amines reacting with ketones. Under acidic conditions, we're going to expect to get what's called an enamine. Okay, so the first one was imines. Now this is enamines, and enamines look like this. So it's a nitrogen with two R groups, and it's kind of like an enol in a way. It has that double bond just off of the carbon to another carbon there, just one carbon away. So how does this happen, right? It's not intuitive until you know the mechanism. So let's get into that. So ketone here, it's going to follow kind of similarly. So we have our ketone. It's going to pick up a hydrogen from solution. Okay, and that just becomes an activated carbonyl. You've heard it a million times now. I won't bother to reinstate why that's important. We get nucleophilic attack from our secondary amine. So it's going to kick up electrons and it's going to swap charges. Oxygen has the positive charge, now nitrogen has it. So let's show that. Nope. Okay, so nitrogen now has a positive charge. How can we make nitrogen happy? Well, we can do a simple step of deprotonation. So let's take some of our secondary amine as a base and deprotonate. So now we get a tertiary amine here. Now what happens is, okay, oxygen is now wanting to leave, so we want to kick out that hydroxyl group. So it's going to pick up a hydrogen from solution, make that water leaving group that we saw last time. Okay, and now nitrogen is like, okay, I'll kick you out, right? Nothing we haven't seen. But I want you to notice a difference here. Okay, so we lost water, and now we have this positive amine-like thing. But is it a protonated amine? No, it's not. Look how we can't just deprotonate, right? When we look at the imines, for example, we saw this scenario, right? This is a protonated amine. This is not. Okay, notice how in this structure, all we had to do was get rid of the hydrogen, and then we'd have a neutral structure. Here, we can't just take a base and remove a carbon group. That's just not how chemistry works. Okay, so something else needs to happen, and that's why you get an enamine. Okay, so instead of deprotonation, we can't go by that step to neutralize the nitrogen's positive charge. So what we have to do instead is take base and do elimination. Weird, ain't it? But it's the only way you can neutralize that positive charge. So we take some of our basic secondary amine, and we're going to do elimination and kick up the electrons to the nitrogen. Okay, that's kind of clever, ain't it? Look at that. We neutralized a charge by doing elimination. That's exactly what happens, and that's why you get an enamine. So that's secondary amines reacting with ketones under acidic conditions, is it forms an enamine. Let's just go through the mechanism once more. So we have our ketone, picks up an acidic proton, then that amine attacks, the secondary amine attacks, kicks up the electrons, makes a hydroxyl group. We neutralize the positive charge on the nitrogen by deprotonation. Then water is going to just randomly pick up a proton from solution, forming a water leaving group. Nitrogen kicks that out, right? It swaps the charges, okay? We lose water. And then we're going to get enamine formation by elimination to neutralize the positive charge. So now I want to get into one more little topic called wolff-kishner reduction, which is very synthetically useful. So let's get into that. So the next reaction we're going to look at here is called the wolff-kishner reduction, okay? And basically, I want you to follow the scheme here. The overall scheme is we go from ketone to alkane, right? We're going to have two H groups there. Weird, ain't it? But basically how this works is we take a molecule called hydrazine, which looks something like this. So it's NNHH. It's basically like if you stuck two ammonias together, right? Looks like that. So you take that molecule and you react it with H2SO4 with a ketone. It makes a hydrazone. Okay, a hydrazone looks like this. Okay, and then you use potassium hydroxide, H2O, and you heat the solution up and it just gets rid of itself. What you'll notice is it actually loses nitrogen gas. Okay, that's important. So let's get into the mechanism here. I won't bother to look at the formation of the hydrazone. Just treat this like an R group if you were asked to draw a mechanism, and you'll get the same thing, right? It follows that primary, because in theory, like, that is a primary amine right there. So it does primary amine attachment. So let's start with our hydrazone. And I'm going to elaborate the hydrogen bonds here. Now, what happens first is we're going to take a molecule of hydroxide. We're going to attack a hydrogen. We're going to protonate, or we're going to give electrons to nitrogen. Nitrogen's going to take, or actually, let's draw the intermediate first. It probably happens all at once, but let's say that it happens like this. So we'll draw H. So I have a negative charge on the nitrogen. We're going to push that negative charge onto a carbon, which is like so cursed, but it happens. We push it onto this bond, so make a double bond with the nitrogen, and then we're going to take these electrons and put it onto the carbon. So what we see, and Lord forgive me for drawing such a cursed mechanism, that you've never seen before, most likely, but we get a negative intermediate. Now, what happens? We're going to take the water. Now, that water is close by, right? We had our hydroxide. It forms water. We're actually using water as a solvent, too, but it's close enough to the molecule where as soon as that transfer of charge happens, it's going to come right back with this hydrogen and get deprotonated. So we form hydroxide again. We form hydroxide again, right? So this is OH minus when it leaves. And we're going to get this structure here, all neutral. So the next step of the mechanism, I'm actually drawing the hydrogen here so you can see. There is a hydrogen in this spot. So the next step of this mechanism is to then deprotonate again to form a nitrogen gas leaving group. So how this happens is exact same process. OH comes in, deprotonates, makes our nitrogen negatively charged. And let me draw that better. So the same thing will happen here. So notice that this has a negative charge. It's going to push electrons like this. But notice, we're not breaking a double bond where we're going to keep that attachment. No, nitrogen's like, I'm done. I'm done. If I'm getting kicked out, if I'm getting a third bond, you're getting kicked out. Okay? So that's exactly what happens, and we get a carb anion, and we're going to get nitrogen gas as a leaving group. So it bubbles out of solution. Once you get to this step and the gas gets released, well, you have no more, there's no way of reversing this process, right? Because it's a gas leaving. So we then will see that this will just simply get protonated by our water, leaving us with an alkane. So we went from hydrazone to alkane. That's the mechanism. Very synthetically useful. If you need to get rid of a ketone on a relatively simple molecule that won't be interfered by any of these other chemistries, which, you know, when you get to the bigger molecules, it's not so much. It's kind of tricky, but, you know, it's a very useful tool. Like if you had, like, I don't know, you had a benzene ring with a ketone on it, and then you had this, and you wanted to make it a phenol, for example, you could do this chemistry and you just get rid of this, and oh look, you have phenol now. Stuff like that. That's where the Wolff-Kishner reduction really comes in handy. I hope you guys enjoyed. Please like, subscribe, comment if you learned anything. In the next episode, we get into sulfur nucleophiles.